orders. The integrated rate law. How to derive them. And what I would say is you could expect something like this in an exam or a midterm, right? It's being able to determine the reaction orders, the rate, and so on, given data like this. Now we didn't finish this. The third question was find the rate of the reaction at a concentration A of 0.15. What do you do there? Well, we didn't actually finish the second question either. We figured out that the reaction order is 2, right? For the first part of the question. So this is the rate law for this reaction. Now the second question says determine the rate constant, that's K. How do we do that? Well, we can, yes? Correct. We can just pick any one of these 4 pieces of data and plug it into the rate law. So let's take the first one. The rate, let me just erase some of this if I may. So that's basically going to go now. We have now figured out that the rate law is Ka squared, K concentration of A. Remember I said A, I'm talking about concentration. So I can also plug something in. So the rate, it says 0.2 equals K. A is the concentration of A, which is 0.01 squared. So K is going to be 0.2. What is that? That's 1 over 100 squared, which is how much? Well, that's 0.01 squared. Can someone calculate that? 0.2 over 0.01 squared. Yes, and I'll provide one.
Okay.
You will be provided with a standard scientific calculator. All right, so what's the value of K? Anyone? What? 2,000. 2,000. Now, what are the units? What are going to be the units of this guy? Yes, per second. Very good. All right, let's just check that. I just saw a very nice thing here of the units and the units. Oh, sorry, it's moles per second. Right, so if it's zero order, it's moles per second. If it's first order, it's per second. If it's second order, it's per moles per second. So moles per decimeter cubed. So per moles per second. And then you have a nice overview of this. And then you can see other variations.
Why is tomatoes raised more?
Because that means 1 over s to the power of 1. S to the minus 1 is 1 over s.
Moles per second.
It's per moles per second. Well, it's not moles. It's capital N means moles per decimeter cubed. It's molarity. So then let's just write this properly. It's 1 over moles per decimeter cubed second per second. That's what it is. So if you write it like that for it's just per moles per second. Second to the minus 1, moles per decimeter cubed to the minus 1. That's the unit for a second. Those are the units for a second order reaction. First order reaction is just per second. not the units of K, rate constant. And zero order is just moles per second. So if it's zero order, it would be moles, not moles per second, moles per decimeter cube per second, which is capital N. The capital N here represents, you see moles per liter or moles per decimeter cube. Remember I said to you earlier, decimeter cube is the same as a liter, so you can use that. Or you can. So those are the units.
Decimeters cube, is that the third or
Moles per decimeter cube is moles del dm to the minus 3, or moles over dm to the power of 3. 1 over x is the same as x to the minus 1. Moles over dm cubed is the same as moles times dm to the minus 3 moles per decimeter. Yes?
Why isn't it this
Because I've written it underneath the line. And if I take it out, and if I write that, you guys don't know how to work with exponents on the street.
the actual notation of decimeters cube is to the negative third?
Well, per decimeter, right? So that's moles dot dm cube. Look, this is the unit for concentration for capital N. The unit is moles per decimeter cube. You can alternatively write that. That's exactly the same as moles per liter, like a liter of milk. 1 liter is 1 decimeter cube. I could write this guy as moles point dm to the minus 3. If I take the decimeter cube out, it becomes decimeters to the minus 3. That's the preferred way of writing it because we use scientific notation. I can write this as moles dot liter to the minus 1. Scientific notation, exponents. Yes?
Why isn't it just seconds though? Isn't it 0.2 moles per decimeter cube and 0.1 moles per decimeter cube per second? So those two cancel out and just be seconds?
No, because it's squared.
Okay.
You see, it's 0.2 over 0.1 to the power of 2, so you're left with a moles per decimeter cube, that's why. All right, so that's basically that. How we do that. Okay, now we've got the rate constants, it's 2,000. And the next question is, find the rate of the reaction at a concentration of 0.15. Or should say find the initial rate of the reaction if I have a concentration of 0.15 moles per liter, moles per decimeter cubed of A. What would we do now? Well, we've now got K. So we can now say rate, the rate law is 2,000 A squared. Okay? So to determine the rate at a concentration of 0.15, what are we going to do? Correct. Not 1.10. And then you plug that into a calculator. That would be the rate. That would be the rate of the reaction at that concentration. All right, let's move on. What I want to just talk about now is collision theory, theoretical models of chemical kinetics. And what this is all basically about is, as you can see there, it is based on the occurrence of collisions, a so-called collision frequency, between molecules causing an observed chemical reaction, causing a reaction. Now think about it. If you have two molecules that bounce against each other, right, they're only going to form new bonds. In other words, new chemical bonds, i.e. a reaction, is only going to take place when the orientation of those two molecules is in the right orientation. For example, it could be that if you've got two linear molecules and they bounce off each other, like there's no reaction takes place, and then only takes place if they, let's say, bounce off each other in an orthogonal way, you know, or depending on the situation. Now, that's basically what this all boils down to, is the probability of the right collision taking place. Now, what is going to improve your chances of having the right collision taking place, do you think? In other words, increasing the rate of the reaction. Temperature and pressure, concentration. Now, basically what you have for all molecules, right, you have a distribution of kinetic energies at a certain temperature. And that, well, this is just, before we get there, this is just to highlight what I was just talking about. Let's say we want these two, here we've got N2O reacting with NO, forming nitrogen and NO2. This is the reaction. In this case, let's say for argument's sake, the reaction only takes place if the O and the N collide with each other. If you've got two molecules colliding with each other in this fashion, no reaction takes place, or if the nitrogens collide with each other, no reaction takes place. Those are unfavorable conditions. The fact of the matter is these molecules are bouncing off each other all the time. Think of them as gases. It's the easiest way. But it's the same thing in solution, in the liquid state. And of course, to increase the probability that you have a favorable collision, temperature, pressure, concentration helps your chances. Now, what we basically, if we look at, this is a distribution of kinetic energies of molecules at certain temperatures. Now, what you basically have is, let's imagine a room full of gas molecules. The temperature of this room is roughly 298 Kelvin, right? Does that mean that at this temperature, all the gas molecules in this room have exactly the same kinetic energy? In other words, the same speed? Yes or no? No. Some are moving faster, some are moving slower, but there is a certain proportion of them that have a certain speed. So let's imagine this blue curve is the kinetic, a representation of the fraction of molecules having a certain kinetic energy at room temperature, right? So you can clearly see that, forget about the pink curve for a moment, you can clearly see that some molecules, gas molecules, have a preferred kinetic energy, but there's a distribution of kinetic energies. Now, if I increase the temperature, what's going to happen? What's going to happen is this pink curve here. This is called a Boltzmann distribution, right? It's a Boltzmann distribution. We're going to increase the fraction of molecules having a higher kinetic energy. Do you see that? So this, remember, this y-axis is the fraction of molecules having a certain kinetic energy